Today we're going to be looking at a really cool problem which was first published by the American mathematician Ralph Palmer Agnew back in 1942, and it's still reasonably famous even today, so it's certainly stood the test of time. And the problem is this. Sometime before noon, it starts to snow at a steady rate. A snowplow, which clears snow at a constant rate, sets off at noon. It has covered 2 miles by 1 p.m. and 3 miles by 2 p.m. At what time did it start snowing? If you'd like to try and solve the problem, then pause the video now and I'll reveal the solution in a few seconds. Well, we're not given very much information to start us off, but we want to find the time that it started to snow. So let's say it started snowing big T hours before noon, where T is greater than 0. And next, well, the first thing we're told in the question is that it snows at a steady rate. So we can reasonably assume that the depth of the snow is going to increase linearly with time. So we can write an expression for the snow depth as a function of time, where a is some constant that we aren't told. Next, we're told that the snowplow clears snow at a constant rate, which means that its speed is going to be inversely proportional to the depth of the snow. So therefore we can write the speed as 1 over the snow height. We could introduce another constant here to represent how many units of snow our snowplow can clear per unit of time, but since we have the constant a from the snow height, we don't need to. It wouldn't really change anything, it would just make it a bit less tidy. Okay, so that's good so far, but what we're interested in is the distance covered by the snowplow, and distance is just the integral of speed with respect to time. When the speed is constant, that simplifies to speed multiplied by time, but here the speed isn't constant, so we need to integrate. Now, let's give ourselves some room to work this integral out, and here I'm using z as a dummy variable for the integral. It doesn't have to be z, it can be whatever you like. The important part is that the limits of the integral are from 0 to t. So we can integrate this, and we get 1 over a log of t plus z. Then evaluating this at the limits, we get the difference of two logs, which we can combine using the fact that log x minus log y is just log of x over y. And then we can tidy this up, and that's our expression for the distance travelled as a function of time. By the way, if we solve a step that you were stuck on, then go ahead and try the rest of the problem from this point on. I always find that maths problems are much more rewarding when you've had a good go at them yourself instead of just being told the solution. Anyway, we have two unknowns, a and t, and how are we going to solve for those? Well, using the two boundary conditions that we're given. We know the distance covered is 2 miles and 3 miles after 1 hour and 2 hours respectively, which we can write like this. Now, big T is what we want to know, and we can quite easily eliminate a from these equations by dividing one of them by the other, which gives us this. So finally we have an equation for t that we can solve. Let's start by multiplying to get rid of these fractions, and then to remove these logs, we want to take the exponential of both sides. And when we do that, these coefficients outside the logs become exponents. So we can expand these brackets, cancel terms, and multiply both sides by t cubed, and then we're left with a nice quadratic equation that we can solve. Now, this gives us two solutions, and one of these is clearly negative, but since we said that t has to be positive, we're only interested in the positive one, which happens to be 1 over the golden ratio, phi. So our answer is roughly 0.618 hours before noon, or about 11:23 a.m. And that's the answer to the question found. But we never worked out the actual value of A, which we need to know if we want to know the distance the snowplow has travelled at any point in time. But we can plug our solution back into the first boundary condition and rearrange it to find A. Then we can substitute this back in for A, and we have our final formula for the distance as a function of time. I think this is just such an elegant problem to think that this final answer with natural logs and phi, the golden ratio, all arises from such a simple question with so little information given to you. It's really no wonder that this problem is still around 80 years after it was first written. Anyway, if you solved the problem, very well done. It's far from easy. And if you couldn't manage it, I hope you learned something from the video. That's all for now, but since we had a snow-themed problem, I thought I'd leave you with this photo of my dog enjoying the snow, or just being a little bit confused by it maybe. As always, if you'd like to see more videos like this, please subscribe, and if you've got any suggestions for things you'd like to see in future videos, please put those in the comments down below. Thanks for watching, and I'll see you next time.